In this video, we're going to learn about CPU quota. It's an alternative and very different way to constrain the amount of CPU that our container uses. For multi-threaded applications, which most Java applications are, this can have some dangerous ramifications, which we'll see. CPU shares were a relative value, and that can be quite complicated to reason about. So CPU quota is an absolute value. We can actually dictate exactly the number of microseconds that our application will be allowed to run per period. So when we use CPU quota, we also have to set the period for that quota. We set the CPU quota to the number of microseconds of CPU time that a container can use in a CPU period. And the default CPU period on most Linux machines is 100 microseconds. And once your time is up, it's up. You'll be throttled. The container won't be allowed on the CPU. This can be quite dangerous if you're building a latency sensitive application. So how do we set this with Docker? Well, just like we could set CPU shares directly when starting our Docker container, we can also set CPU quota and period. There is a shorthand for it in later Docker versions, which is CPUs. We used that in a previous video to limit our container to 10% of a CPU to 0.1. And what that did under the covers was set CPU quota and CPU period based on the number of cores. So for example, you could set, if you wanted to give your application the equivalent of 1.5 cores, you could set the CPU period to 1 second and then your CPU quota to 1.5. And what that means is your container will be allowed to use 1.5 seconds of CPU per second. Now, the only way you can do that is if you have more than one CPU. Otherwise, it's impossible. The big gotcha, which will mention more than once in this video, is that you can use up your CPU quota very quickly if you have a multi-threaded application. So if you were to be allowed 1 second of CPU time every second, you would suspect that you get one core and your application would always be able to run on that core. But if you have 10 threads running using 10 cores, you can actually use up your CPU quota in 1/10 of the time. So think about that. You have your Java application, you think you've allotted one CPU to it with CPU quota and a CPU period of 1 second, but then 10 threads use up all of your CPU quota in the first 100 milliseconds, in the first 1/10 of a second, and then your application will be throttled for 0.9 seconds because you've used up all of your CPU quota. That's why I think it is quite dangerous to use CPU quota for multi-threaded applications. So what will Java do if you've got CPU quota set? Well, we've already seen what happens if we have CPU shares. But assuming you're on the latest version of Java 8, or you're on 9, 10, 11, 12, then CPU quota overrides the shares calculation. So if you've got a CPU quota set, it will work out what the equivalent CPUs is. So some examples: 200 milliseconds of CPU quota per 100 millisecond period is like 2 cores, or 50 milliseconds of CPU quota per 100 milliseconds is like half a core. There is a way you can turn this off and prefer to use the CPU shares calculation. And that is with the prefer container quota for CPU. This is set to on by default, but you can set it to off, and then it can still use CPU shares in the calculation. But it does say prefer, so it doesn't completely remove the CPU quota from the calculation. What it does, if you turn this flag off, is it flips to minimum of the calculation based on CPU quota and CPU shares. So this stuff can get complicated. I think a lot of the time we won't set CPU quotas for applications, for Java applications, so we can just set the CPU shares. But if you are setting CPU quota, and we'll see which flags in Kubernetes result in CPU quota being set, then you need to know about this calculation. The big danger of using CPU quota is throttling. And that's because once you use up your quota, then you're not allowed to use the CPU. And the container's CPU quota can be used up in initially surprising ways. So let's run through some examples. So if we set a CPU quota of 100 milliseconds, now the values when you set CPU quota in microseconds, but I think sometimes we'll deal with milliseconds. And we also set the CPU period to be 100 milliseconds. This sounds like one CPU all of the time, right? No, unfortunately not. If we have multiple threads running in our application, we can use up that CPU quota by lots of threads running in parallel on different cores. And then at that point, we'll be throttled. And this can be very common when you've got applications which don't size their thread pools based off the number of cores on the machine. So, things like Jetty and Tomcat, the actual request thread pool is typically a big number because you have one thread per concurrent request. So it's very easy in that style of application to have your application throttled nearly all of the time. So let's jump into a demo and see how the various different JVM versions behave when CPU quota is set, just to make sure we've got that formula right. So for this demo, we're going to use a very similar application as we did for CPU shares. The main things we're going to do is print out the number of cores and then the parallelism of the common pool, the fork join pool. We'll also use a very similar Docker image. We'll just be taking the output of the application plugin and putting it into the Docker image and then putting an entry point for it. So we're just going to use our normal Gradle docker build command. The submodule this time that we're using is CPU quota. So let's build that. So it'll take a few seconds. And now let's make sure the image is built. So we'll just quickly run a docker images and grep for the image name. There it is, CPU quota. So let's try and run it. So first we'll do it without any CPU options. So no quota, no shares, and it's picking up the number of cores that's on the host. Now let's add a CPU period of 100,000 microseconds and a CPU quota also of 100,000 microseconds. So this means we're going to expect the equivalent of one CPU. But of course, we don't get that. We are still using up the resources of the host. And whatever values that we specify for period and quota, we just use up the resources of the host, which of course is not what we want. But that's happening because we're using an old version of Java. Let's update our version of Java and then see how this changes. So the version we need is Java 8 version 191 at least. Now for some reason the OpenJDK only publish an Alpine image for that, so let's use that and then rebuild the image. Okay, so that's done. Let's just make sure it's there and then let's run it with a different set of CPU quota and CPU period values. So there it is, it's Alpine, so it's a bit smaller. First let's run it with nothing and then yep, it picks up 8 cores because that's what the host has. And now let's try some different values. So we'll start off with a CPU period of 100,000 and a CPU quota of 100,000. So hopefully this should show up as one CPU. Now, could you imagine your surprise if you updated a patch release and got this significant difference in behavior? I mean, it would be very shocking and your application would behave very differently in a container. So if you are on an old version of Java and you are going to upgrade and you're in a container, make sure you test with the new behavior. So before we leave this version of Java, let's just run a few more experiments with different values. If we up the quota by just one microsecond, we get an extra core. Or if we set it to 200,000 with a period of 100,000, we also get 2 cores. And we can try this with a couple more values. And as you can see, the number of cores just keeps moving up when we increase the CPU quota. And the final test is just to have a look at the behavior in Java 11. So we'll rebuild our image as always because we've changed the base image to Java 11, and then we'll run some of the same experiments. So first, let's just run it without any, and then yep, we get 8 cores as we expect because we haven't provided any CPU shares or CPU quota. And then let's just quickly run through the experiments to make sure the behavior is the same on Java 11 as it is on Java 8. Yep, that works. So now let's see what happens if we set CPU shares and CPU quota. So with the current settings, the CPU quota would give us 2 cores, and the equivalent CPU shares would be 2048, and that works. But which one would it pick if we had different values? And you can see if we change the CPU quota, but we leave the CPU shares the same, it ups to 3 cores. So CPU quota is king. It will override the value of CPU shares. Now, because we're on Java 11, we can, with one flag, change this. And because of the script we use with the application plugin, we can provide an environment variable with some Java options in. And the Java option that we're going to pass in is the prefer container quota for CPU count. And we're actually going to turn that off because it's on by default. The negative before the option name turns it off. Now, if we were to specify a CPU quota that should give us 5 cores, but CPU shares which should only give us 2 cores, you can see it's now picking the CPU shares. So if you prefer the CPU share based algorithm, then you can specify this flag or turn this flag off. A final note, all of what I've talked about before are the calculations built into the JVM to behave based on what CPU shares and what CPU quota has been set. There's now a flag which allows you to completely override this for processor count. So if you want to pick a different algorithm, you can wrap the start of your application, inspect the things that we've seen, like the sysfs cgroup file system, and then make your own decision based on how many cores you want your application to use. So this comes to the end of our section of the course on container CPU. So hopefully now you have a good understanding of how CPU shares and CPU quota can affect your Java application. I definitely suggest coming back to these videos anytime that you need a refresher, particularly when trying to work out how container CPU works inside Kubernetes, or if you've got any unexpected latency blips for your Java applications running inside containers.